Hello, everyone. We're the Tabor factor group, and today we're going to present for the predictive maintenance Tabor factor determination as a function of strengthening mechanism in copper. And the presenters are Anton, Saketh, Nicholas, Erin, and Derek. Next slide, please. So why is predicting mechanical failure important? So what is mechanical failure? Mechanical failure is when the material breaks down due to mechanical forces. Mechanical failure means failure due to a defect in materials or workmanship. Mechanical failure does not include failure due to normal wear or improper machine application and or maintenance. So what is predictive maintenance? So PDM is a set of monitoring tools along with data analysis through machine learning and statistical analysis to predict when equipment is going to fail and needs repairs. What are the methods of mechanical failure forecast? The mechanical failure forecasting involves techniques like condition monitoring, visual inspections, and non-destructive testing through hardness measurements, for example. So can we predict UTS from localized hardness measurements? The ultimate tensile strength can be estimated from localized hardness measurements, and for steels and cast irons, this relationship is well established with respect to Brinell hardness. In general, the ratio between hardness and strength is what is called Tabor factor.
The Tabor factor is the relationship between the hardness and strength of a material. It is hardness divided by the strength. It was originally from theoretical physics from David Tabor, reporting that the Tabor factor was approximately 3, and refined solid states physics from J.R. Cahoon reported the range to be around 2.9 to 3.1. Neither of the original theoretic papers made any assumptions regarding the crystallinity, bonding, or microstructure. Microstructure is usually a micron scale structure of a material defined as the structure of a prepared surface of material as revealed by an optical or electron microscope. This is not the atoms, but the actual structure of the material. Next slide. In 1950, Hall and Petch established the relationship between grain size and crystalline metals and the strength. This is known as the Hall-Petch or HP equation. It has a direct relationship between the grain size and the yield strength of an alloy. The HP equation tells us that we can achieve greater strength if materials have smaller grain sizes. So this reduction of grain size is a strengthening mechanism for crystalline metals. The aims of our research are to measure the ultimate tensile strength and Wicker's hardness as a function of grain size to determine the Tabor factor for pure metal copper. We also plan to conduct extensive literature search for copper to find the ultimate tensile strength, yield strength, and hardness data as a function of grain size to estimate the Tabor factor. We plan to compare our measurements with data available from the literature. Why copper? There is a large amount of data on copper microstructure in relationship to the strength as seen available in the MIT article, 6 Decades of the Hall-Petch Effect. Copper is inexpensive, especially in comparison to silver and gold and other types of materials like that, and is commonly used, especially in manufacturing, despite being relatively understudied.
Before etching, the copper is heat treated to make the grains larger and easier to view. So samples are put in the furnace and heated to 800 or 900 degrees Celsius for about an hour. And during this time, a control thermocouple, which is like an electric thermometer, is kept inside the crucible to monitor the process. Next. So once the samples have cooled down, they have to be polished to remove the black oxide layer formed during heat treatment. So currently we're manually polishing using sandpaper, starting with a 400p grit and working up to 60,000p. and a polished sample will have a mirror-like appearance. Next. Etching is the final part of the process to reveal the microstructure. After polishing, the samples are immersed in an etching solution consisting of 1 part nitric acid and water for 5 to 15 seconds. However, we've found that 12 and 15 seconds are optimal. Samples are then submerged in deionized water to stop the reaction, and then dipped in methanol to prevent residue formation. Next.
So once these samples are all processed, we have to characterize them and observe them. Firstly, we have our metallurgical microscopes to observe the grain boundaries and the grain microstructures. We use the Nikon and Olympus optical microscopes, which are very useful for observing these grain microstructures. We also have the Keyence digital microscope, which creates a digital image and allows for analyzing the height and distance measurements on the screen and on the computer. We are also using the Vickers hardness test to determine the Tabor factor of our samples, which is a micro hardness test with a force of 1 Newton. This is a micro hardness test and compares the samples on the Vickers hardness scale as opposed to other macro hardness scales such as the Burnell and Rockwell scale. And it uses a pyramid-shaped probe to indent the samples and measure the hardness. We are also 3D printing a model of these microstructures so we can better observe them and visualize them. As you can see on the right, we have a basic sketch of the plan of what we are going to do to print them and put them together. Also, to the right of that is the 3D printer, which we are using to print these unit cells. And these are all going to be put together into one model. However, it will have some gaps in it where the unit cells do not fit together. These are the grain boundaries, and we will use clay or Play-Doh to fill these in. We are still working on this, but right now our proposed layout is 8 cubes, 8 rectangles, and 6 triangles. These are some of the unit cells that we are printing and are going to print. We have the FCC 100, FCC 110, and FCC 111. And here's our progress so far of the model that we are printing. We have not finished yet. However, this is a basic design of what we're going to do.
Right, so here are the results for our heat treated samples. And so here you see that we have heat treated samples at 900 degrees Celsius, and it was etched in a copper in a solution of 0.5 molar nitric acid for 15 seconds. And on the left 4 images, you see that there is pretty good you could see the grain boundaries pretty well. But on the right hand side, you'll see that there are a lot of polishing marks going like across, and that's something we're going to try to improve on. Next slide. Yeah, so here are the results for our 800 degrees Celsius treated samples, and it was etched for 12 seconds. And here you can see that the grains are a lot more visible. Next slide. So sample preparation has to be improved to move on to the next stage for quantitative metallurgical work. We will perfect our procedures and write up a standard procedure for using the Buehler auto polisher, and by using polishing cloth with alumina suspension for a mirror finish. We're going to try and change the etching copper procedure by monitoring time with a stopwatch and rinsing it in the deionized water for longer times to make sure the etching process really stops. And we're going to organize our samples and then store them in a desiccator to prevent the etching from like disappearing. And on the right hand side, you'll see that we have a Buehler auto polisher. Next slide. So we learned how to polish copper samples manually and with the auto polisher, and we concluded that copper heat treated at 900 degrees Celsius is etched in 15 seconds, and copper heat treated at 800 degrees Celsius is etched for 12 seconds. And we found out that the copper heat treated at 800 degrees Celsius provides the best results so far. We learned how to observe copper grains with the metallurgical microscopes. The best method for polishing is the use of auto polisher from coarsest to roughest or to finest grit and hold firmly. And the next step is to you begin with vigorous hardness measurements. As you see on the right-hand side, we have a vigorous hardness machine. Next slide. So here are our future plans. We'll continue to finish the 3D model you saw earlier. We will begin using new copper samples more fit for the auto polisher and begin using a polishing cloth with aluminum suspension to decrease presence of polishing lines, and we hope to achieve a mirror finish. We'll also repeat the heat treatment at 700 degrees Celsius. So we have 3 sets of sample or data to choose from for each grain size. We're going to learn how to measure grain size from optical images of the microstructure. We're going to learn how to perform vigorous hardness tests. And what we really need right now is a tensile machine to test and measure UTS.
These are our references.
Yeah, so we'd like to acknowledge ASDRP, parents, and Dr. Starostina for giving us this opportunity. Now, are there any questions?